Hello, so today we would like to discuss how to solve forward kinematics problems. So what is forward kinematics? It is a specific problem in robotics, and given the individual state of each joint of the robot in a local frame, we can compute the position of a given point on the robot in the global frame. And usually that point is the end effector point. In this class, we have several assumptions of the robot. So our robot is a kinematic train made of rigid links and movable joints. There will be no branches or loops, and all joints have 1 degree of freedom. So the joint will either be a revolute joint or a prismatic joint. Here's the formula we use to solve for kinematics. First, we want to compute the zero position M, and that's the zero configuration matrix. And for each joint I, we define the screw axis. And for each motion of a joint, we define the screw motion. That's the S right here. And we would like to solve that in later problems. So here's the formula of the homogeneous transformation matrix. To solve the matrix, we would like to first compute the zero configuration matrix M. So M is composed of two other matrices, and R is the rotation matrix from the space frame to the end effector frame, and P is the position of the new frame. We also want to compute the screw motions. In that case, we actually have two cases. So case 1 is a revolute joint. In this case, the norm of the omega will be 1, and V equals to negative omega cross product Q plus H times omega. In our class, the pitch will be 0, so it's actually the formula right here, V equals to negative omega cross Q. In the second case, where our joint will be a prismatic joint, we don't really need to consider omega, so the norm of omega will be 0. And the norm of the V will be 1. And the axis of the movement defines the value of V. Next, we'll work through an example problem right here. As you can see, the space frame is x0, y0, and the end effector frame is defined by x1 and y1. There are three joints in the problem. One is the prismatic joint, and the other two are the revolute joints. First, we want to compute the M of the M in this problem. So as you can see, the end effector frame is 8 units away in x-axis from the space frame, and it's 4 units away on y-axis away from the space frame. To get the rotation matrix, we will first like to set up two coordinates using right-hand rule right here. As you can see, x1 is the negative y0, and y1 is the x0, and z1 is just 0, z0. In that case, we can form the M matrix of this problem. Next, we will discuss some methods to determine the direction of the rotation or the translation. First, we'll talk about the revolute joint. As you can see, the symbol of the revolute joint in our problems are a rectangular or a circle right here. The direction of rotation is determined by the positive direction of the rotation. It's actually decided by the direction of the arrow according to the right-hand rule. And this arrow points towards the side that has link. And the direction of the translation of a prismatic joint is also determined by the direction of the arrow. In this case, it's pointing towards the smaller rectangular right here. I will show you how to compute S. So the joints start from joint 1 right here. We start from the space frame. So the first joint is a prismatic joint, and Since it's a prismatic joint, the omega doesn't really matter, so we will just set it as 0. And then V1 is just the direction of the translation. It's in the negative x-axis, so it will be negative 1, 0, 0. Then we can just set up S1 like this. So S1 is formed by omega 1 and V1. Next, we want to calculate the revolute joint. So as you can see, the direction of rotation is pointing downwards to the negative y-axis. So omega 2 is 0, negative 1, 0. And the position of the second joint is negative 4, 0, 0. Then we can calculate the V2 by using the formula V2 equals to negative omega 2 cross Q2. So we can also get S2. To compute the third joint is very similar to how we calculate the second joint. Since its direction of rotation is also pointing downwards to the negative y-axis, its omega 3 is 0, negative 1, 0. And Q3 is negative 8, negative 2, 0 right here. Then we can calculate V3 by using the formula V3 equals to negative omega 3 cross Q3. So we can get S3 in this case. With the 0 configuration matrix we calculated before and these 3 screw motion matrix, we can then get the transformation matrix. And here's the reference of the video, and thanks for watching.